Dear students, today I would like to discuss the self-ionization of water, the ionic product of water. Myself, Dr. Digna Varghese. Self-ionization of water. Water undergoes self-ionization to a small extent as given in the equation, that is, you can see here H2O plus H2O in equilibrium with H3O plus OH minus. That means water undergoes self-ionization to give hydronium ion and hydroxyl ion. The equilibrium constant for this ionization is given by K is equal to concentration of H3O plus into concentration of OH minus divided by concentration of water molecules. Therefore, we may write K into H2O square is equal to concentration of H3O plus OH minus. Since the degree of ionization of water is very small, concentration of H2O may be regarded practically a constant value. So we introduce another constant in the place of K into H2O square, that is Kw, where K is equal, Kw is the K into H2O square is equal to Kw. Therefore, Kw is equal to concentration of H3O plus into concentration of OH minus. Do you know the term Kw indicates? That is, Kw is the ionic product of water. So, Kw is the ionic product of water. So, it is equal to the molar concentration of hydronium ion into molar concentration of hydroxyl ion. Now we are going to discuss ionic product of water in detail. Ionic product of water represented by the term Kw, that is equal to the product of the molar concentration of hydronium ion and molar concentration of OH minus. So, the definition of ionic product of water is that it is defined as the product of molar concentration of H3O plus and OH minus at a given temperature. That is very important. Kw has the value of 1 into 10 raised to minus 14 mole square in per liter square. That is equal to 1 into 10 raised to minus 14 molar square at 298 Kelvin. From the definition itself said that it is defined as the product of the molar concentration of hydronium ion and OH minus at a given temperature. That is very important, at a given temperature, because Kw has the value 1 into 10 raised to minus 14 molar square at 298 Kelvin. If it is a different temperature from the 298 Kelvin, the value also will be different. Ionic product of water with temperature. From the table you can see the temperature and its corresponding value of Kw. Unit is molar square. That means mole square per liter square. What is a molar? That is 1 mole per 1 liter. Okay. And at 298 Kelvin, that we know the value of Kw is 1 into 10 raised to minus 14 molar square. At 303 Kelvin, 1.5 into 10 raised to minus 14 molar square. At 313 Kelvin, 3 into 10 raised to minus 14 molar square. So we can see from the table, as the temperature increases, the ionic product of water also increases. So at a particular temperature, the ionic product of water is a constant. As the temperature increases, the ionic product value also increases. So Kw is increased with increase in temperature. Ionic product of water with pH. In pure water or in a neutral solution, Kw is equal to H3O plus into concentration of OH minus. We know the ionic product of water value is 1 into 10 raised to minus 14 mole square per liter square at 298 Kelvin. That means in pure water or in a neutral solution, the concentration of hydronium ion is equal to concentration of hydroxyl ion, that is equal to 1 into 10 raised to minus 7 mole per liter or 1 into 10 raised to minus 7 molar at 298 Kelvin. In acidic solution, we know the concentration of H3O plus is greater than the concentration of OH minus. In basic solution, we know reverse is the case, that is concentration of hydroxyl ion is greater than concentration of H3O plus. That means concentration of hydronium ion is less than concentration of hydroxyl ion. In any case, the product of concentration of H3O plus and the concentration of OH minus, that means the ionic product of water is a constant at constant temperature. So we can say that Kw is a constant at constant temperature, irrespective of whether the solution is neutral, acidic or basic. We have seen that the acidity and alkalinity of a solution depends upon its hydronium ion concentration and hydroxide ion concentration. We know that for acid solution, hydronium ion concentration is high. For a basic solution, the hydroxyl ion concentration is high. These concentrations can vary within very wide limits. And in dilute solutions, the values become quite small, so that they have to be expressed as the negative powers of 10. That is the pH scale. The pH scale is introduced by Sorensen. Soren Peter Lauritz Sorensen was a Danish chemist. He is famous for the introduction of the concept of pH, a scale for measuring the acidity and alkalinity. The acidity and alkalinity of a solution depends upon its hydronium ion concentration. The pH scale is the convenient method in expressing the hydronium ion concentration of a solution. The pH of a solution is defined as the negative logarithm to the base 10 of the value of the hydronium ion concentration in moles per liter. That is, pH is equal to negative logarithm to the base 10, the value of concentration of hydronium ion in moles per liter. So we can calculate pH is equal to minus log concentration of H3O plus. The pH of a solution is defined as the negative logarithm to the base 10 of the value of the hydronium ion concentration in moles per liter. At 298 Kelvin for pure water or in a neutral solution, the concentration of hydronium ion is equal to concentration of hydroxyl ion. So its molar concentration value is equal to 1 into 10 raised to minus 7 mole per liter, that is equal to 10 raised to minus 7 molar. The pH at this for this solution is 7. So it is a neutral solution or a pure water. For an acidic solution, the concentration of hydronium ion is greater than concentration of hydroxyl ion. Here, the concentration of hydronium ion is greater than 10 raised to minus 7 molar. Hence, pH is less than 7. For a basic solution, the hydronium ion concentration is less than hydroxyl ion concentration. So, the hydronium ion concentration is less than 10 raised to minus 7 molar. So, the pH is greater than 7. Since we know the calculation of pH is equal to by using the equation minus log 10 to the base concentration of H3O plus. It can be easily seen that concentration of H3O plus is equal to 10 raised to minus pH. pOH scale. The pOH scale expresses the hydroxide ion concentration. The pOH of a solution is defined as the negative logarithm to the base 10 of the value of the hydroxide ion concentration in moles per liter. pOH is equal to minus log 10 to the base of molar concentration of OH minus. So we can write in this way also. Concentration of OH minus is equal to 10 raised to minus pOH. pKw. The ionic product of water is defined by Kw is equal to the product of molar concentration of hydronium ion and hydroxyl ion. The negative logarithm of Kw to the base 10 is called pKw. Therefore, pKw is equal to minus log 10 to the base Kw. At 298 Kelvin, the value of Kw is equal to 1 into 10 raised to minus 14 molar square. Okay. Hence, we can calculate the value of pKw, that is equal to 14. Taking the negative logarithm on the both sides of the equation, Kw is equal to concentration of H3O plus into concentration of OH minus is equal to minus log Kw is equal to minus log H3O plus minus log OH minus, that is equal to minus log Kw that we know pKw is equal to minus log H3O plus minus log concentration of OH minus. We know minus log H3O plus is equal to pH minus log OH minus is equal to pOH. Therefore, we can write in this way pKw is equal to pH plus pOH. We know the value of pH plus pOH is equal to 14. From the equation, pKw is equal to 14. So, pH plus pOH is equal to 14. From this, we can calculate if the value of pOH by 14 minus pH and so on. Thank you for your attention.